Yes, I am Raghavan, chemistry faculty from All Force College. Welcomes you for All Force Chemistry e-learning classes, session 11. In this session, let us work out some numericals on Planck's quantum theory and photoelectric effect. Planck's quantum theory. Let us take the Planck's quantum theory numericals. Numericals on Planck's quantum theory. In previous session, we completed the theory part of the Planck's quantum theory. Now the numericals on Planck's quantum theory. Okay, let us take up. 100-watt bulb gives a monochromatic radiation. 100-watt bulb. Let us take the first numerical. 100-watt bulb. 100-watt bulb gives monochromatic radiation. That means it is giving out monochromatic radiation of 400 nanometers wavelength, of 400 nanometers wavelength. Okay, so what we have to find in this? Calculate number of photons. Calculate number of photons. Calculate number of photons. So wavelength is available and energy is also available. We have to calculate number of photons. Okay, first calculate energy of one photon. Okay, so now 100, that is energy is given as in the form of 100 watt. 100 watt is equals to 100 joules. That means 1 watt is equals to 1 joule per second. Okay, we should not forget that it is 100 joule per second. That is 100 watt energy. Okay, now let it be like that. Now lambda is given 400 nanometers. We have to calculate number of photons. Now energy of one photon, energy of one photon is equals to, energy of one photon is equals to, that is E is equals to h nu. We know that E is equals to h nu, or nu is equals to c by lambda. We know that E is equals to hc by lambda. So therefore it is hc by lambda. hc by lambda. Therefore h is the Planck's constant, that is 6.625. Okay, let us consider only 6.62 into 10 to the power minus 34 joule second into velocity of light 3 into 10 to the power 3 into 10 to the power 8 meter per second by lambda is given as 400 nanometers. 400 into 10 to the power minus 9 meters. 10 to the power minus 9 meters. Okay, so on solving this we will get the answer. Approximately it is 4.97 into 10 to the power 4.97 into 10 to the power minus 19. Yes, joules. That is the energy on one photon. This is energy on one photon. Now number of photons we have to find. This is energy on one photon. Now number of photons is equals to number of photons is equals to total energy, that is 100 joule second. 100 joule per second by energy of one photon 4.97 into 10 to the power minus 19 joules. That is approximately, that is 100 by 4.97, that is minus 19, positive. 20.12 into 10 to the power 19 photons. This many number of protons are present in the given energy light. Okay, once again, the complete concept of the numerical is a 100-watt electric bulb. It is emitting a monochromatic light. That means a light of single wavelength. How much wavelength? 400 nanometers. So how many photons are emitted from the monochromatic light? That is 100-watt bulb. So as we know that 1 watt is equals to 1 joule per second. 1 joule per second. Okay. Now energy of bulb is 100 watt is equals to 100 joules per second. That we know. This is the data is available for us. Next, let us calculate energy of 1 photon, that is E is equals to h nu or E is equals to hc by lambda. Now substitute the values. Lambda, Planck's constant value, that is 6.62 into 10 to the power minus 34 joule second into velocity of the light 3 into 10 to the power 8 meters per second divided by 400 nanometers, that into 10 to the power minus 9 meters. So we are getting energy of 1 photon is this much, and we have to find the total number of photons in the present bulb, electric bulb, that is number of photons in 100 watt bulb, number of photons in 100 watt energy, that is equals to number of photons in 100 watt energy, that is equals to, that is 100 by, this is energy of 1 photon, total energy by energy of 1 photon, that is equals to this many photons are present in the given energy light. Okay, that is one numerical on this. Okay, now let us calculate. Okay, let us compare another concept. Let us take up, compare the energies of two radiations. Okay, let us compare the energy of two radiations. Let us do that. Yes, energies of two radiations. Yeah, energy of two radiations. Question, let us prepare like this. Compare the energy of two radiations, one with wavelength 400 nanometers, one with wavelength 400 nanometers, and another with lambda 2 is 800 nanometers, one with 400 nanometers and second one with 800 nanometers. 400 nanometers and 800 nanometers. We have to compare their energies. Compare the energies of this. So as we know that E is equals to hc by lambda. Fine. That is a basic equation for us. Now E1 is equals to hc by lambda 1. Okay. Similarly, E2 is equals to hc by lambda 2. Okay, done. Now the ratio of energies E1 by E2 is equals to, that is equals to hc by lambda 1 into lambda 2 by hc. Okay, yes, that is E1 by E2 is equals to lambda 2 by lambda 1. Okay, this is the necessary relation for us now. So therefore, so E1 by E2, that is equals to lambda 2 800 nanometers by 400 nanometers. Okay, and it is 1 2s and it is 1, that is equals to 2:1. The energy ratio of the two radiations having wavelengths 400 nanometers and 800 nanometers. So the energy ratio is 2:1. Okay, this is like this. We can expect some simple numericals. Okay, it is in terms of nanometers. Okay, so we can also expect to calculate energy ratio in terms of frequency, in terms of per seconds, that is frequency, relation with frequency. Let us find out like this. E1 by E2, that is equals to nu1 by nu2, because it is directly proportional to the frequency. Okay, and energy with respect to wave number E1 by E2 is equals to nu bar 1 by nu bar 2. So like that we can find out the energy ratio with respect to wavelength and with respect to frequency and with respect to wave number. Like that we can find. Okay, and the number of photons also we know that already we had the discussion about it. So E is equals to NH nu. N is the number of photons, H is the quantum, that is photon energy, H is the Planck's constant, and free, that is nu is equals to frequency of the light. Okay, so we can also work like this. E is equals to N H C by lambda, because nu is equals to C by lambda, we know that. So by using this data, that is, these are the two constants, and when lambda is available and energy is available, we can calculate number of photons using this. Okay, energy, number of photons using this. Right, fantastic. Next, energy with wave number relation, that is E is equals to HC nu bar. We can also use this. Nu bar is the wave number, that is a relation with energy and wave number relation. Okay, like that we can calculate various types of numericals for all competitive examinations. Okay, not only for EAMCET, the basic fundamental is common for all the examinations. Once you are strong in all the fundamental concepts, so automatically you can build, you can understand the content of the given problem and you can answer them. Okay, now let us take up another problem. Okay, this is second problem we have done, and coming to the next, let us go to the next problem, that is let us write. Okay, next problem, let us work out on photoelectric effect. Okay, photoelectric effect. The theory content is completed in the previous session, that is now photoelectric effect. Once let us define what is a photoelectric effect, then we can go into the numerical. Okay, photoelectric effect, that is, this is the surface of a metal. So the surface of a metal, it contains its own number of atoms on the surface, and the atom has its own electron. Now we are concentrating the surface. This is, say it is one atom and this having its electron, that is surface atom electron. Okay, now certain photon light is falling on the metal surface, certain photon light. Okay, that means it is having its own energy. E is equals to H nu, that is light is falling on the metal surface, so that is called incident light. Okay, it speaks about incident light. E is equals to H nu, or we can say E is equals to Hc by lambda, frequency of the incident light, wavelength of the incident light. Completely this is representing incident light which is falling on the surface of metal. Okay, now this surface electron is not free on the surface. It is bounded to the surface by some attractive forces. It is binded to the surface by some attractive forces. So now to eject this electron, surface electron, we have to provide some amount of energy to this. Okay, this surface electron absorbs some part of this light. Okay, the surface electron absorbs some part of the photon energy. Then the electron is ejected from the metal surface. The electron is ejected from the metal surface. Then the remaining energy is released as kinetic energy of the photoelectron. Kinetic energy of the photoelectron. Okay, so this is absorbing some part of this energy. So that is E naught is equals to H nu naught. E naught is equals to H nu naught. Or we can say E naught is equals to Hc by lambda naught. What is this? It is the amount of energy absorbed. Amount of energy absorbed. Absorbed energy. Absorbed. Okay, it speaks about completely absorbed. It speaks about complete incident, that is incident Incident light, absorbed light, electron is ejected and remaining energy is released as kinetic energy. That is the content. Okay, fine. So once again, some part of the photon light falls on the metal surface. The surface electron absorbs some part of the photon energy light, then the electron ejected from the metal surface. The remaining other part of the energy is released as kinetic energy of the photoelectron. Okay, so simple understanding. For example, 100 joules energy light is falling on the surface. The surface electron is absorbing 40 joules energy light is absorbing. Some photon light is absorbing. Okay, and electron is ejected. Then the remaining energy means 60 joules energy is radiated, that is in the form of kinetic energy. Okay, got it. 100 is equals to, that is incident light, the total energy of the incident light is equals to sum of the E naught, that is called absorbed light. This absorbed light is called threshold energy, or it is also called work function. Absorbed, that is threshold energy, or it is called work function. Threshold energy is nothing but E naught. Work function is, it is represented as W. You can use any symbol, it is not a problem. Okay, the concept of this is like this. So that is, as we know that E is equals to E naught plus kinetic energy, or E is equals to W plus kinetic energy. Okay, so we can construct so many numericals on this. Okay, so many numericals. It's a very beautiful concept for all the competitive examinations. It is very, very important. Okay, now let us go ahead with this. Okay, now let us work on one numerical. Let us write. Okay, what is that concept of how we can prepare the numerical? Say threshold energy for a photoelectron emission, from the surface of a metal is, threshold energy for the photoelectron emission from the surface of a metal is 4.9 into 10 to the power minus 19 joules. Okay, that means how much energy is required? E naught is given, that is E naught is equals to how much? Let us remove this. Okay, once again let us see the concept of the problem. Threshold energy for the photoelectron emission from the surface of a metal is 4.9 into 10 to the power minus 19 joules. That is, E naught is given clearly. E naught is equals to 4.9 into 10 to the power minus 19 joules. It speaks completely threshold energy. Okay, done. Threshold energy is given like that. Okay, next, calculate threshold energy is given. Calculate the threshold frequency of the ejected electron. Calculate threshold frequency of the ejected electron. That means E naught is given. He is asking you to calculate nu naught. Okay, so therefore we can say E naught is equals to this much. Then we are finding nu naught. Okay, that we are calculating. Say E naught is equals to H nu naught. E naught is equals to H nu naught. So therefore we can say nu naught is equals to E naught by H, that is threshold energy by Planck's constant. Okay, right, very good. Okay, the concept is very simple and important. Then E naught is equals to given 4.9 into 10 to the power minus 19 joules. Okay, divided by the Planck's constant value. What is the Planck's constant value? 6.625 into 10 to the power minus 34 joules. Okay, so joule second. So now joule get cancelled. That is equals to 4.9 by 6.625 into 10 to the power minus 19. So that approximately it is equal to 0.74 into 10 to the power 15 per second, okay, or that is equals to 7.4 into 10 to the power 14 per second. That we can calculate like this. So that is, we calculated the threshold frequency of the light. Okay, like this we can calculate threshold frequency here. So the data is available only the absorbed light. That means work function, or rather you can say threshold energy. Threshold energy of the light is given. How much? It is 4.9 into 10 to the power minus 10. That means, so by absorbing this much of energy, the electron can be ejected from the metal surface. Okay, when the electron can be ejected from the metal surface by absorbing this much of energy, what is its threshold frequency? That we calculated like this. Okay, this is the concept of the problem. Okay, now let us consider another problem, that is same. Let us make out one more problem based on this. Okay, so that for practice, right, for better practice, let us work out one more example on this. Okay, right. The problem we can make like this. The threshold energy of a photoelectric material. The threshold energy of a photoelectric material. The threshold energy means it is nothing but work function E naught of a photoelectric material. That means the surface electron can be ejected by absorbing some amount of energy, that is E naught. The threshold energy of a photoelectric material is 3.3 electron volts. It is given 3.3 electron volts. Okay, that much of energy is absorbed, that is required to eject the surface electron from the metal. So what is its threshold frequency? That means the same concept, but it is, the question is prepared in a different manner. That is, the threshold energy in the previous, it is given in joules, now it is available in electron volts. So calculate its threshold frequency. Again the same concept is repeated. Okay, let us, yes. So as we know that 1 electron volt is equals to 1.602 into 10 to the power minus 19 joules. You should be very careful about it. Okay, so therefore E naught is equals to 3.3 into 1.602 into 10 to the power minus 19 joules. Now it is converted into joules. It is in the form of joules now. Okay, now what we have to take? V in nu naught. Nu naught is equals to E naught by H. We know this. Yeah, substituting this. So nu naught is equals to, nu naught is equals to how much? That is E naught. How much it is? E naught is equals to, it is already given, 3.3 into 10 to the power, that is 3.3 into 1.602 in terms of joules, 602 into 10 to the power minus 19 joules by H is Planck's constant value, 6.625 into 10 to the power minus 34 joules. Okay, now nu naught is equals to, that means threshold frequency is equals to, it is joule second. Okay, so it goes per second, it becomes, now nu naught is equals to 0.7979 into 10 to the power minus into 10 to the power 0.7979. Okay, 4. Okay, done. 15. 10 to the power 15 per second. 10 to the power 15 per second. That is, so or we can say 7.979 into 10 to the power 14 per second. That is the final value we can write. Okay, that is threshold frequency of the light. Okay, once again the concept of the problem is the threshold energy of a photoelectric material is 3.3 electron volts, they said. Okay, 3.3 electron volts. What is its threshold frequency? So that is simple calculation we can do like this, and we have to remember that one point is 1 electron volt energy always it is equal to 1.602 into 10 to the power minus 19 joules. We should remember such constant values. Okay, so the example is clear. It is clear. The example is clear. It is not a difficult one. Okay, then next one is next problem. Let us take up. Okay. Okay, let us make out one more numerical. So one more numerical, let us discuss about it. Again, this from the same photoelectric material only. Let us take up. Okay. Right. In photoelectric emission, okay, or in say you can say in photoelectric effect, the energy of photon striking, yes, let us prepare like this. Okay, in photoelectric emission, okay, in photoelectric effect, the energy of a photon striking the metal surface is, that means E is 5.6 into 10 to the power minus 19 joules. 5.6 into 10 to the power minus 19 joules. This much of energy is striking the surface of the metal. Okay. Calculate the kinetic energy of ejected electron. Okay, or no, let us prepare like this. The kinetic energy of the ejected electron is, let us say it is 1.2 into 10 to the power minus 20. 1.2 into 10 to the power minus 20. 1.2 into 10 to the power minus 20. It is in joules. Okay, calculate work function. Okay, calculate work function. See, for easy calculation, let us make it is not 1.2, make it 12 into 10 to the power minus 20. Now we have to calculate work function. Now it becomes easy, simple calculations. That is, as we know that total energy is equals to work function plus kinetic energy. Now you are calculating, that is work function. Okay, now work function is equals to W or E naught. Work function is equals to E minus kinetic energy. That is total energy minus kinetic energy. Okay, where W is equals to what? Work function, that is equals to total energy. It is nothing but E naught. Remember, okay, don't get confused with this. So it is E naught, that is nothing but work function. So this is total energy minus kinetic energy. So what is that? Total energy is given. The total energy is given as 5.6 into 10 to the power minus 19, okay, minus 12 into 10 to the power minus 20. So that is equals to, that means work function is equals to, so it is approximately subtracting this, how much you will get? 6.4 into 10 to the power minus 19. Okay, so subtraction, you will get the work function, that is in joules. subtracting these two. So this is kinetic energy and it is total energy. That means in photoelectric effect, the energy of a photon striking the metal surface is this much. This much energy photon light is striking the metal surface. Okay, then the kinetic energy of the ejected electron, that means the electron is ejected with this much of kinetic energy. So then what would be the energy absorbed by that electron? That is work function. What is the amount of energy required to eject the electron? That is work function. Now we are calculating. That is work function is equals to total energy minus kinetic energy. So subtracting this, you will get the answer. Okay, so this is simple problem. Okay, right, thank you.